So about 1 million years ago, we did convergent and divergent plate boundaries. And the last plate boundary type we're going to talk about is less common, at least along the ocean, but it's probably one of the ones you've heard of frequently, at least in terms of earthquakes. That's transform plate boundaries. Transform plate boundaries, the figure that I have right here is the one that's in your book. It's a really good one. And it's figure 226 in the one book and 2.23 in the slightly older book. So just find this picture in there. And what usually happens is there you have a mid-ocean ridge, which in this diagram you can see here and here. And because we're wrapping, basically rock around a sphere, it fractures and we get, it shatters. And the mid-ocean ridge itself is, the fracture zone or the transform fault occurs right in here, as where the plates are slide perpendicular to the crest of the mid-ocean ridge. And if you were to look at them, they frequently have a zigzag appearance. You can see it in this area. You have ridge, and then you have fracture zones kind of going along them. And it's what gives the appearance of stitches on a baseball. So transform plate boundaries have that specific shape to them, that zigzag. Even though they are more common in the ocean, as in an oceanic transform fault, continental transform faults probably get more press because the most famous one, at least in this country, is the San Andreas Fault. And the San Andreas Fault can be seen at the bottom of this picture right in here. And we have two different plates. We have the North American plate and the Pacific plate sliding past each other. So you can actually see the plates. And we have a pretty cool picture of it. I think it's this next slide. This is actually the San Andreas Fault as it moves through part of the desert. And you can see the actual fracture zone, which then also goes on and fractures itself. We have the fracture zone, and then there's like all the little cracks. Looks pretty cool. Transform boundaries. The earthquakes tend to be very shallow, right at the surface, but they tend to be very strong. The moment is 7 in the ocean, but on the land it can actually be very strong, 8.5. That's what we're talking about when we talk about the big one in California, is the big earthquake between the San Andreas Fault. And what's kind of interesting is this is actually, in terms of plate movement, fairly fast. What the San Andreas Fault, the west side is moving northward at a rate of about 5 centimeters per year. And what this means is if you look at the cities San Francisco and LA, they're in either side of the fault. But San Francisco is stationary and LA is moving slightly northward. And in about 18.5 million years, they'll be in the same spot, which is kind of a cool factoid. While we're talking about the faults, I suppose I'll throw this in here where we talk about Neptune. The Ocean Bowl kids will be really familiar with this, but basically there are these underwater observatories, and they like to name these ocean observatories after planets for some reason. But there's Mars, Venus, Saturn, Pluto, no Jupiter, at least not so far. And the benefit of an underwater observation station is that it's permanent. So that what they do is they put all these sensors out in an array along some interesting area, the Juan de Fuca, which is where Neptune is. And there's cables that go back. And what that gives you is real-time measurements of things that are going on. You don't have to go out on a boat. You don't have to wait for a satellite to be overhead. It gives you constant observation abilities. And because of that, the cost per amount of data you get is actually lower than it would be if you go out on a boat. The Neptune has actually been in the news a lot lately because the Juan de Fuca ridge has become very, very active in the last couple of years. And there's actually, in terms of the concerns about plate tectonics on the West Coast, is kind of shifted away from California now to the Juan de Fuca. The Juan de Fuca is not likely to cause like a large transform fault type earthquake, but is more likely to cause potentially a tsunami. And if you can see in the background picture, the Juan de Fuca is so close to Oregon and Washington State that people are really concerned. So there's been a lot of talk about that lately. What we're talking about in this last section in the book, which I'm sure you all read, is that so we now have this model of plate tectonics, and based on this model, if it's correct, it should be able to explain all of the features we see on the seafloor. So we're going to talk about a mantle plume and a hotspot. Now the hotspot is, the classic hotspot is Hawaii. And this picture is a really good one for you to take a minute and really look at. But basically, the idea is that there's this plume of magma coming up. And this plume of magma, we don't know why it occurs where it is. Plate tectonics, for all its awesomeness, cannot explain why the mantle plume occurs. It's entirely possible that it's due to convection cells underneath the plate having some anomalies. But Hawaii is a really famous one. So it's an island. Now, we talked about when we did convergent plate boundaries, island arcs. You need to be able to tell the difference between an arc, a series of islands that are an island arc, and a series of islands that are due to hotspots. So let's talk about this for a minute in terms of Hawaii. There's some other famous hotspots, by the way. Yellowstone is another one. And there's Iceland and Galapagos are not hotspots. Those are actually due to edges of plates. Those are island arcs. So Hawaii is kind of a famous one, and basically it's a chain of islands that's mostly oriented along the northwest and the southeast. And there's a chain of volcanoes. The ones that come above land we call the Hawaiian Islands. And then there's the Emperor Island Seamount, which is the same chain, but it's mostly underwater. And it's formed by, there's this plume of magma that you can see in the picture here that's coming up over the surface. And that spot stays in one spot all the time. That hot spot is a spot. It doesn't move. But the plate moves over the top of it. So the plate is moving this way. It's moving in that direction. So over the top of the hot spot. And when whatever part over the plate is directly over the hot spot, we get an active volcano. Right now, that's the Big Island in Hawaii. And it's the Big Island because it's actually biggest because it's being constantly supplied with magma. As you move away off of the hot spot towards the northwest, the islands get older and smaller. And that seems weird. Why would they be getting smaller? Well, magma, as it cools over the centuries, is it shrinks. It gets more dense. So not only do they subside slightly, there's also erosion, and there's also, if you were to look underwater, a bunch of chains of volcanoes that don't come above the water surface anymore. And there's actually a new one. The Big Island is moving off the hotspot, and there's a new island called Lohi that is going to break the surface probably in the next 1,000 years. Oh, and a word you need to know. This chain of extinct volcanoes, the Emperor Island Seamount chain, is the correct term for that, is a nematoth. And we'll talk about this more in class, and how you can get plate movement direction. So the seamount is an underwater volcano. They may be extinct, but they don't come up above the water surface. If they do, we call them an island. Okay. So what you should take away from this picture is that you can kind of see it in this image in two spots. So let's talk about Hawaii first. You can tell that this that we have a specific plate movement. This is old at this end, and it's newer at this end. Since we know the hot spot doesn't move, we can tell that overall the plate, at least for the duration of the Hawaiian Islands, has been moving to the northwest. Make sense? But if you look, this is actually all one chain. And this part is not moving to the northwest. Back when this was over here, the plate was moving due north. So now the plate moves this way. Millions of years ago, or to be precise, it used to move north. And you can tell that from this image. What's interesting is a lesser known chain of Pacific Islands has the same thing. We have the McDonald Seamount, which is the newest one. And then we have this old nematoth over here. And if you notice, same kind of idea, right? For the last 40 million years, been moving northwest. Both of them before that were moving primarily north. So it's kind of an interesting thing to take away from this picture in terms of the nematoth and the direction. Hint, hint, this might be a question. We'll finish with coral reef development and eventually the Wilson cycle in the next video.